In the previous class, we were discussing about the asynchronous SRAM. Here, the RAM and ROM. There are different types of the memories. RAM means random access memory. ROM means read-only memory. Here, the random access memory can be classified as SRAM and DRAM. SRAM and DRAM. Static random access memory. DRAM means dynamic random access memory, like this. I will show you here in this slide. Yeah, okay. Memory, okay, random access memory, read-only memory. Okay, the random access memory can be classified as asynchronous static RAM, synchronous static RAM, and dynamic RAM. Okay, first here we'll discuss about the asynchronous SRAM. First we'll discuss about the asynchronous SRAM. In the previous class we were discussing about that. Here it's a simplest form of memory. Okay, and why it's called asynchronous? Because it is not dependent on clock for its timing. Not dependent on clock for its timing. Here we know that SRAM is volatile memory. Here what is meant by the volatile? Why it's called static? The term static means that the stored data persists indefinitely so long as power is applied to the memory component. Okay, it is volatile memory, meaning that it requires power to maintain the stored data and loses data if power is removed. Okay, if the power is removed, okay, it loses the data. Okay, asynchronous SRAM internally uses 1-bit storage cell that are similar to the delatch circuit. Okay, and here within the memory component, the address is decoded to select a particular group of cells are enabled that comprise one locations. Okay, here during the write operation, the selected latch cells are enabled and the input data is stored. Okay, here the asynchronous SRAM, which consists of a 1-bit storage cell. 1-bit storage cell. Here when we enable those cells, okay, input data is stored. During the read operation, for a read operation, the address activates a multiplexer that routes the outputs of the selected latch cells to the data outputs of the memory component. Here we have the memory, within that we have the latch cells. Okay, here we can select the memory locations from where from which locations we can fetch the data, we can read the data. Okay, that is done by the multiplexer that routes the data, routes the output of the selected latch cells to the data outputs of the memory component. And also we discussed about that the asynchronous SRAMs are available as packaged integrated circuits. Available as packaged integrated circuit, just like IC. Okay, then not as blocks in ASIC libraries or FPGA. They usually have bidirectional tri-state data input output pins. Okay, next here we will discuss about the symbol of asynchronous SRAM. This is the symbol of asynchronous SRAM. This is a symbol. Okay, here A. What is A? It indicates address. D, data. C, E. It is available as a chip, right? That's why chip enable signal. W, E, which can this signal is used to enable read and write. Okay, one more is OE, output enable. Okay, here just note down here, chip enable input is used to enable or disable the memory chip. Chip enable input is used to enable or disable the memory chip. Second one, WE bar. Right, see a bubble. Okay, that means it's a bar, a complement. Okay, the CE bar, WE bar, OE bar, output enable bar. WE bar, write and enable input, controls whether the memory, if enabled, performs a write or read operation. Okay, one more. Next one is output enable input. The output enable input controls the tri-state data drivers during a read operation. Okay, which can controls the tri-state data drivers during a read operation. When OE signal, OE bar is low during a read, the drivers are enabled and can drive the read data into the data output pins of the memory. Okay, when OE bar is high, the drivers are in high impedance state. What is meant by the high impedance state? Which can retain the same previous data when the OE bar is low. Okay, here these are the waveforms for write operation and read operation. Okay, this indicates the address. Okay, then chip enable, that means it is 0, this plot here. Okay, then WE bar, when the WE bar is low, it's a write signal. Just remember, this one is low here, low, it's a write signal. Just remember that. Okay, during the read operation, what will happen? See here, during the address, during read operation, this plot is same. That's why I written same. Okay, same, and chip enable also same to perform the read and write operation. Here, during the write operation, WE bar is low. During the read operation, it's high. It is 1. Here, 0. Okay, that is the difference. Then one more is OE bar is high. Okay, we already discussed in the during the read operation, OE bar is low, which can enable the tri-state drivers to drive the data to the memory output pins. See, that's why we kept low. Which one? OE bar. Then the last is the output. Here the stored data, okay, which can be hold. That means here OE bar, which will not drive the output data, which can be retained as it is. Okay, here the whatever the stored data can be read data. That means read means which can fetched, which can be fetched. That is about the write operation and read operation. We have to go through this block diagram. See here, during the write operation, what we will discuss same as. During the write operation, control section selects the particular memory chip by driving C bar low. C bar is low here. Yes. Then activates the write operation by driving WE bar low. WE bar is low during the write operation and ensures that the chip's tri-state drivers are disabled by driving OE bar high. The data is stored transparenting in the latch cells for address location. For the particular address location, okay, just remember what are the signals we use during the write operation, either it is 0 or 1. Please check it. Control signals. C bar is low. I'll show you here. C bar is low, then WE bar is low, and OE bar is high. If OE bar output enable signal is high, means drivers are disabled. Okay, this is about the write operation. Okay, during the read operation, what is the only difference here? Let's go through here. What is the difference? WE bar is high, YE bar is low. That is the difference here. See, the read operation, only difference is that the WE bar signal is held high. See, this one is high, and the YE bar signal is driven low. That means YE bar signal is low and WE bar is high to enable the memory chips tri-state drivers. Okay, the read operation is essentially a combinational operation involving decoding the address and multiplexing the selected latch cells values onto the data outputs. This is about the read operation. Okay. One more thing is here, it's very important. Just note down this point here. ASRAM are usually the internal storage cell of SRAM or SSRAM are same as that of the asynchronous SRAM. Internal storage cell. Okay. The asynchronous SRAM consists of that cell, right? Okay. Same thing. The storage cells of the SSRAM are the same as those of the asynchronous SRAM. Is it audible? Hello? Reply? Anyone? Given associated with asynchronous SRAM, many memories implementation fabrics provide synchronous SRAM. Okay, we simply call it as SSRAM. Okay, the internal storage cells of SSRAMs are the same as those of the asynchronous SRAM.
Hello.
Hello. Hello. Hello. storing the address, input data, and control signal values, and in some cases, output data. Here, the interface of the SSRAM, which includes clock register for storing the address, input data, control signal values, and in some cases, output data. Here, we have some different types of the SSRAM. One is flow-through SRAM. Flow-through, flow-through, flow-through SRAM. You see, the simplest form of SSRAM is called a flow-through SRAM. It includes registers on input. It includes register on input, but not on the data output. Please remember this. It includes registers on the input, but not on the data. The term flow refers to the fact that data read from memory cell flows through directly to the data output. There is no tri-state driver here. Okay. In the asynchronous SRAM, we have tri-state drivers. Okay. Okay. Using that tri-state drivers, we send the data to the data output. But here, on output, okay, on the memory output, we don't have registers. The registers on only the input. Registers on only on the input, but not on the output. Okay. Why we call it as flow through? The flow through refers to the fact that data read from memory cell flows through directly to the data output. Okay. Having registers on the input, having registers on the input allows us to generate the address, data, and control signal values according to our clock synchronous design methodology. Having registers on the input allows us to generate the address, data, and control signal values according to our clock synchronous design methodology, ensuring that they are stable in time for a clock edge. That means why it's called synchronous? It's clock based. Okay. Having registers on the input allows us to generate the address, data, control signal values according to our clock synchronous design methodology, ensuring that they are stable in time for a clock edge. Here, just remember timing diagram for a flow through SSRAM. Okay, why we call it as the flow through SSRAM? Here, when during the read operation, the output data can be directly flow through the data output. There is no tri-state drivers, multiplexer, and all. Okay, directly it can flow through the data output of the SSRAM. That's why we call it as flow through SSRAM. It is a simplest form of SSRAM, only which has registers on input, not on the data output. Okay, then this is the timing diagram for a flow through SSRAM. Okay, just remember here. Let's go through this portion. Okay, this is clock 1, clock 2, and clock 3. Clock 1, clock 2, this is clock 2, clock 3. Address register, address A2. Okay, 10. Memory 1 and clock to 6. Okay. Address is A1. Memory address includes clock 3 11 address is 10. Okay. See here during the clock.
We use the asynchronous SRAM. That is the disadvantage of asynchronous SRAM. That's why we go for the synchronous SRAM. Given the difficulties associated with asynchronous SRAM, many memory component vendors and implementation fabrics provide the synchronous SRAMs, otherwise known as SSRAMs. The internal storage cells of SSRAMs are the same as those of the asynchronous SRAM. The storage cells, that means latch cells of SSRAM, same as the asynchronous SRAM. Okay. Then, however, the interface includes the interface includes clock register for storing the address, input data, and control signal values, and in some cases output data. Okay, the interface includes the clock registers for storing the address, input data, and control signal values, and in some cases the output data also. Here we are discussing about the different types of SSRAM. Synchronous SRAM. Why it's called synchronous? It is clock based devices. That's why we call it as synchronous. Okay. First type of SSRAM is flow through SRAM. Flow through SRAM. Here, in the read operation of this one. In the read operation of, I'll show you here. In the read operation of asynchronous SRAM, okay, read operation of the asynchronous SRAM involving decoding the address and multiplexing the selected latch cells value onto the data outputs. Directly, we will not drive the read data to the data outputs here in the asynchronous. Are you getting? Hello? Is it audible? Hello?
Yes, sir, it's audible.
Yeah, okay. See here, in asynchronous SRAM, whatever the read data, it cannot be directly send it or flow through the data outputs of the memory. Okay. Through tri-state drivers, we can use it here to flow the read data to the data outputs here. See here, decoding the address and multiplexing the selected latch cells value onto the data outputs. Just remember this in asynchronous. Okay. In synchronous SRAM, the first type of SSRAM is flow through SRAM. The simplest form of SSRAM is called a flow through SSRAM. It includes registers on the inputs but not on the data outputs. Just remember, this is very important, this point. The flow through SRAM, which includes the registers on the inputs but not on the data outputs. Okay. The term flow through refers to the fact that data read from memory cells flows directly to the data outputs of the memory, data outputs of the SSRAM. Okay, there is no registers. Here the data can be read, then it can be stored in the registers. Okay, but here that read data will not be stored because we don't have registers on the output side. Registers on the output side. That's why whatever the read data, which can be directly flow through the data outputs of the memory. Okay, having registers on the input allows us to generate the address, data, and control signal values according to our clocked synchronous design methodology, ensuring that they are stable in time for a clock edge. It's completely clock based operations. Okay, the registers on the input allows us to generate the address, then data and control signal values. Generate the address, data and control signal values according to our clocked synchronous design. Later we'll discuss the brief explanation about that. See here. This is the timing diagram for flow through SSRAM. Okay, this is clock 1. Clock 1, clock 1, clock 2, clock 3. Address A1, see address A1 came up to clock 1 to clock 2. Address A2, clock 2 to clock 3. Okay, see here, during clock 1 and during clock 2, right signal is high. That means, what it mean? Right signal high means right signal is enabled, right operation is enabled. The right signal is low, that means read operation. This one is read, this one is W. Okay, write operation. Okay, D in XX, the data is stored in the XS registers. Okay, during read operation, data is read directly to the data outputs of the memory. Okay, brief explanation about this timing diagram. See here. During the first clock cycle, we set up the address A1, control signals, and input data in preparation for write operation. See here. During the clock 1, input A1, the control signals are enabled. Enable is high, which can enable the read and write operation. Okay, then write signal is high. That means write operation is started. Then this data can be stored within the cell. Okay, that's why these values are stored in the input registers on the next clock edge, causing the SSRAM to start the write operation. Here, during the first clock and second clock edge, the data here during the first clock, that memory you can set up the values, address values, control signal values, and input data value. Okay, the next clock edge, which can start the write operation. The data is stored and flows to the output during the second clock cycle. While that happens, we set up the address E2 and control signals in preparation for a read operation. For the read operation, we set up the A2 address. Okay, enable signal is high and write signal is low. Write signal is low, enable is high, and we set up the address A2. That is the preparation for read operation. See, when it is during the second clock cycle. Again, these values are stored on the next clock edge, and during the third cycle, the SSRAM performs the read operation. During the third cycle, the SSRAM, which can perform the read operation. The data denoted by M of E2 flows through from the memory to the output. Okay, just remember this one. When enable signal is 0, what it mean? The memory is in idle state. Now in the third cycle, we set the enable signal to 0. This prevents the input registers from being updated on the next clock edge. So the previously read data is maintained at the output. This is about the flow through SSRAM. Okay, this is the type of synchronous SRAM. Shall I explain once asynchronous SRAM? Hello, anyone? Please, anyone reply?
Yes, sir.
Shall I explain once again? See here.
Yes, sir.
Yeah, okay. The asynchronous SRAM is a simplet form of memory. Okay, here it is a volatile memory. Why it's called volatile? It is volatile meaning that it requires power to maintain the stored data and loses data if power is removed. Okay, and also asynchronous means it's not clock based devices, clock based memory. Okay, then asynchronous SRAM internally uses 1-bit storage cell that are similar to the delatch circuit. Okay, then here asynchronous SRAM are usually available as packaged integrated circuits. Okay, and not as blocks in R6 libraries or FPGA. Okay, and they usually have bidirectional tri-state data input and output pins. Okay, this is the symbol of asynchronous SRAM, which has the input pins address, data, CE bar, WE bar, YE bar. A stands for address, D stands for data. Okay, CE bar is used to enable or disable the memory chip. Okay, WE bar, write enable input, controls whether the memory, if enabled, performs a write and read operation. Then one more is OE. OE stands for output enable input. Controls the tri-state data drivers during a read operation. Okay, during the output when it is low, OE bar is low, the tri-state data drivers during a read operation. When OE bar is low during a read, the drivers are enabled and can drive the read data into the data pins. Okay, when OE bar is high, the drivers are in high impedance state. These are the timing diagrams for write operation and read operation. Okay, this is the address. I'll show you. I will use the marker here. This is the address. Okay, CE bar is low. That means which can enable the memory chip enable. WE bar low. That means write operation. OE bar is high. Okay, the tri-state drivers are off. It's in high impedance state. Then this is stored data. Just remember this. Okay, during the read operation, same address we have. Then chip enable is low. Then WE bar high. It's 1 here, 0. OE bar is low. Enable the tri-state drivers to drive the data, read data to the output lines. This is about the read operation. Just remember that. Okay. Then one more thing here, we can use asynchronous SRAMs only for low performance devices where their low cost is the benefit. That is one more important here. Where we can use Asynchronous SRAM are usually used only in systems with low performance requirements, where their low cost is a benefit. Okay. I hope it's clear. Asynchronous SRAM. Hello. There are two types of SRAM: asynchronous SRAM and synchronous SRAM. Shall I wind up?
Yes, sir.
ಅರ್ಥ ಆಯ್ತಾ ಮಧು?